Good day everyone. So here's a problem regarding the heat conduction. So say let us consider a 2 meter high and 0.7 wide bronze plate. So say this is a bronze plate as the illustration. So the thickness of this bronze plate is 0.1 meter. Okay, one side of the plate is maintained at a constant temperature. Say on this side we maintain a constant temperature of 600 K, while the other side is maintained at 400 K Kelvin. Okay. The thermal conductivity of the bronze can be assumed to vary linearly in the temperature range as so the thermal conductivity of the bronze plate is given as a function of k sub 0 1 plus beta t, okay, where k sub 0 is equal to 38 watts per meter Kelvin, and the beta is 9.21 times 10 to the negative 4 per Kelvin. Okay, so disregarding the effects and assuming steady one-dimensional heat transfer, determine the rate of heat conduction through plate. So we are tasked to determine the rate of heat conduction. Okay, yan. So this is our given problem, and it says here that we assume that the process is in a steady state and one-dimensional. So let's have some illustration of this side with a thickness of 0.1 meter. To simplify our figure, and it says that we maintained a temperature at the surface 600 K, and on this side is, let's call it T2, 400 K. Okay, and the thermal conductivity of this plate is given by the is given by this linear equation. K as a function of t is equal to k sub 0 1 plus beta t. Okay, so using these illustrations and figure, we need to determine the rate of heat conduction through this bronze plate. Okay. For the solution, since we are required to determine the rate of heat conduction, let us use the equation Q is equal to K A delta T over delta X, right? Okay. We're in our based from our problem, we have a given area of 2 by 0.7 meter. So this is our area Okay, and as we imagine, the heat flows from this direction going to this direction. Okay, so we have a Q. So the surface area is 0.7 by 2 meter. Okay, so we have 2 by 0.7 meter. And then our delta T, the change in temperature, is given by this initial condition, the 600 K and 400 Kelvin. So we have 600 minus 400 Kelvin, and our delta X is from this point up to this point is that we have a 0.1 meter as the thickness of the plate. Okay. Okay. So we have now this equation, and let's call it equation 1. And before we can come up with the value of our heat transfer, I mean the rate of heat transfer through conduction, then we need to find the value of our K. Okay. So solving for K, since it is a variable K, then to find the K average, we can use the given linear function K is equal to K sub 01 plus beta T. So we have K as a function of the temperature is equal to K sub 01 plus beta T. So we are talking about the average temperatures here. And the value of K sub 0 is known. So we have 38 watts per mK. 38 watts per mK. As well as the value of our beta. And the value of our beta is 9.21 times 10 to the negative 4 per Kelvin. So we have 9.21 times 10 to the negative 4 per Kelvin. Oops. And it is being multiplied by the temperature, wherein we need to get the temperature, I mean the average temperature. So we need to add the two initial temperatures or surface temperatures divided by 2 to get the average. Okay, so all in all, the value of our K is 38 watts per mK plus this term, I mean multiply by this term, then we can have a 55.5 watts per mK. Okay, so this unit will cancel out, and we will now have we now have the unit of watts per mK. So therefore the value of our K, or the thermal conductivity, is 55.5. Then substituting the value of our K to equation 1, then we can now easily get the value of the rate of heat conduction through the bronze plate. Okay, so we have 55.5 watts per meter K, then multiply by this 2 by 0.7, so we have meter square is the unit. Then 600 minus 400 K per 0.1 meter. Okay. Therefore, the value of our heat conduction through pipe is 155,397 watts. Okay. Okay, so once again, we have this problem, and we need to determine the rate of heat conduction through this bronze plate. Okay, given with these dimensions and surface temperatures plus the um, thermal conductivity of the bronze plate. Okay, then after uh, after representing our problem through the illustrations, then we can now proceed to our solution. And since we need to determine the Q, then we use the Fourier's law, which is Q is equal to Ka delta T over delta X. And then we substitute our given values to our equation, but we need to find the value of K to complete our given equation. Okay. And then to solve for K, we use the given function. Then we've come up with the value of our K, and the value of our K, we substitute it to find the value of our Q. So that's it, and thank you so much.